Okay, so yesterday we learned about vectors and how to take a vector, break it down into its components, how to write that vector in vector notation that keeps the horizontal and the vertical parts of that vector separate. And we learned how to add and subtract vectors. So what we want to do today is we're going to learn how to apply that vector concept to kinematics problems so that we can actually solve kinematics problems using the tools that we created yesterday. And for that, I want to think about those four kinematic equations of motion. Uh, and I want to think about how those are going to operate in this new sort of vector setting. So let's start with the position equation. That's probably the one that we're going to get the most mileage out of in this setting. So this is what we had with the position equation in chapter 2. Now, in chapter 2, things were only ever moving along a straight line, right? So they were only ever moving in the x direction. And so when we specified positions, we always used the letter x to represent that. The idea was, here was the kind of example from the first lecture. Here's a stupid tree. Here's a stupid dude. And the idea was we'd pick some location. We maybe would say, hey, I'm going to call this tree x equals 0. And then the guy might be at x equals 3, and the other guy might be at x equals 5. And the idea is we were always measuring the distance from the tree to the guy. Oh, look, it's a vector. It's an arrow with a magnitude and a direction. So what we're going to do now is we're going to open it up a little bit. What if I have things moving in 2 dimensions? They're not just moving backwards and forwards in the x direction, they're moving in 2 dimensions. So what if, in addition to these dudes, I've got like a bird flying in the air, and I want to specify the position of that bird? Well, instead of drawing an arrow from the base of the tree to the dude, maybe now my position vector is going to run diagonally. So it's this many meters diagonally towards the bird. And that's how we'll specify it. And we don't want to use x to represent this vector because x is usually like just sideways. And we wouldn't want to use y because y is usually just vertical. So traditionally what we'll do is we'll replace all the position references in our equations where we used to have x's, we'll replace them with r's. And we'll call this r my position vector. But notice if r is a vector that points from the origin that I've picked to where I'm looking, r is going to have components in the x direction and the y direction. But wait a second, the sideways part of my position vector r is just what we used to call x. So the reason this worked back in chapter 2 was because we were doing stuff with vectors where they only had x components and these parts were 0. But now this will be just my y part. So the idea is that r is a vector who has components that are just the x and y coordinates of whatever we're talking about. So I can say that r, the vector, would be whatever my x position is in the I hat direction, plus whatever my y position is in the j hat direction. So, kind of neat. And if I wanted to write this same relationship, but do it in kind of a vector sort of way, what I could really do is replace all the x's with r's, and I could say that my final position vector, r, is going to equal my starting position vector. So I'm just replacing this with this, plus my initial velocity is going to also be a vector times t. So I'm multiplying a vector times a scalar. We learned how to do that. That's cool. We can do that. plus 1/2, that's a scalar, times my acceleration, that's a vector, times t squared, t is a scalar. So again, I'm taking a vector, multiplying it by scalars. So this equation we had back in chapter 2, it's still going to work in chapter 3. All I had to do is kind of generalize what we were calling x into something more generic that we're calling r, but it's still going to work. And the other equations of motion, I can do the same trick. So I can say that like v final, the vector, equals v initial, the vector, plus the acceleration vector times t. I could do the same thing with v final squared oops, I'm replacing x with r, excuse me. So it'd be r final minus r initial. So bottom line is I've got places where I'm multiplying vectors times scalars. We know how to do that. All those same equations of motion are going to still work. However, the caveat is going to be that when we're doing these additions, like here, I'm taking v, which is a vector, and I'm adding it to another vector. And when you add vectors, you have to do it component-wise, right? How do we do that, though? You broke them down into their x parts and their y parts, and you did them separately. And so the same thing's going to happen here. We're going to take all these vector quantities we've been talking about, we're going to split them into their components, and we're going to do their components separately. And what happens in the x direction isn't going to impact what happens in the y direction. We can do them individually. So let's see if we can't put this to practice. Let's actually just do a problem, because really all the pieces we have or we need, we already have. So let's kind of do the most generic two-dimensional kinematics problem I can think of. I got a dude, and he's going to kick a football. And let's say he's kicking that football with a diagonal initial velocity of, let's say, 10 meters per second. And what I would like to figure out is how high at its highest point that football is going to go. So I'm looking for that right there. And let's say that I'm kicking it at a 30-degree angle above the horizontal. So I'm not kicking it straight up, I'm kicking it diagonally up, and I want to figure out how high the football is going to go. So on the surface, this looks more complicated, and it is a little bit more complicated than a chapter 2 problem. But at the end of the day, it's not that much different. What's going to happen is we're going to do the same kind of steps. We're going to start with a picture. Got it? Right? I'm labeling as much as I can in that picture. I've got my starting velocity, my starting position. Here's where the ball is going to end up. There's my final position. Now what I've got to do is choose a coordinate system and take inventory of what I know, just like a chapter 2 problem. The difference, though, is that when I take that inventory, all the things that I'm taking inventory of, they're vectors. And they're going to have components. And I'm going to break them down into those components as I do this. So I'm going to have my starting position, which we used to use x, but for a 2D problem, I'll use r instead. So my starting position, my ending position, my starting velocity, my ending velocity, my acceleration, all of those things are vectors. And of course, t, time, is not a vector. So I've got to choose a coordinate system. Somewhere on this picture, I have to call the origin. And before, in one dimension, we were always choosing where x equals 0. Here, I got to choose where y equals 0 also. And I kind of like having my ball start at the origin. I'm going to call this location 0, 0. So this is my x-axis, this is my y-axis, and I'm going to measure all the positions, just like I'm reading a graph, where there's my two axes, there's 0, 0. And so for my starting position, it's going to be 0 I hat, because it's 0, plus also 0 j hat. The x part is 0, the y part is 0. That's super easy. What about the final position? Well, what's going to happen is my football is going to go some distance sideways, but I don't really know how far that is. So it's going to be something I don't know in the x direction. Remember, I hat means x direction. Plus, it's going to be higher than it was before, but I don't know that either. However, what's the goal of the problem? To figure out how high it is. So I'm going to make note to myself that that's the thing that I don't know that I actually want to find. Cool. Now, what about the initial velocity? Well, here's my initial velocity vector. It's 10 meters per second long, and it's diagonal. I'm going to draw it off to the side just so it's easier to see. Now, this angle right here is 30 degrees, and I can break that vector into x and y components. So v initial is going to be something that's less than 10 I hat, and then something else that's less than 10 j hat. I got to find those two components. How do I do that? Sines and cosines. I apologize. I'm having very, very stuffed up. My allergies are killing me today, so I apologize if I sound really stupid when I'm talking. I cannot breathe through my nose at all right now. So I'm looking for the x component. That's the adjacent side of the triangle. And I know that the cosine of 30 degrees will be the adjacent side. That's the x component. I'll call that v initial, but with a subscript x. So this is the x part of the initial velocity over the magnitude, which is 10. So 10 times the cosine of 30 is v initial x. Super easy. That's the square root of 3 over 2. Square root of 3 over 2 is about 0.866 times 10 is 8.66. So 8.66 I hat. Now, what about the j hat part? That's this part. That's the opposite side. Well, I know that the sine of 30 is the opposite side, which is the y component. So v initial y over 10. So 10 times the sine of 30 is v initial in the y direction. Sine of 30 is 1/2. 1/2 times 10 is 5. So this 10 meters per second at a 30-degree angle, when I break it down into vector components, is just 8.66 I hat plus 5 j hat. Super easy. Now, what about the final velocity? Well, I don't know what the final velocity is because they didn't tell me, but I do know this. I know that it's as high as it's going to go when it's here. And so if I were to draw what the final velocity would look like, it can't still be traveling upward, because if it was still traveling upward, it would go higher. And it can't be traveling downward, because if it was already traveling downward, it would have been higher a second ago. So at the highest point, it's not traveling up or down. That tells me that the y component of the velocity has to be 0, but it could still be traveling sideways. So when I do this, the sideways velocity, I don't know. It could be anything. But the up and down velocity has to be 0. So that's just like back when we threw the object straight up in the air. If I'm throwing it straight up in the air, it had no x component. It only had a y component. And at the highest point, the y component was 0. If I'm throwing it diagonally, the y part still has to be 0 at the highest point, but the x part may or may not be 0. That's the idea. Now, what about the acceleration? When I kick that football, I have a football that's being affected by gravity and nothing else. That means it's got to have an acceleration of 9.8 meters per second squared downward. Well, straight down is not sideways at all. The x component of the acceleration is 0. The y component is going to be the acceleration of gravity, which is we use the letter G, that's 9.8, and it's downward, so I'll put in a minus sign. And of course, the time to go from here to here, I don't know. So I've done an inventory, and it's very much like my previous problems where I've got the 6 things I'm tracking. All that's different is that of those 6 things, 5 of them have 2 components, one for X and one for Y. So it's like having, instead of 6 things in the inventory, really it's like having 11 things in the inventory. But it's still the same process. Now what we're going to do is we're going to solve the problem. And we're going to do the same sorts of tricks here that we did previously. Remember, the X component and the Y components are independent of one another. So I can kind of look at those 4 equations of motion and use them separately for each of the 2 sides. So let's see if we can't break this down. What am I looking for? I'm looking for the final position in the Y direction. Now, in the Y part of this inventory, what do I know? I know the starting position, the starting velocity, the ending velocity, the acceleration, and the time. So if I want to solve this problem in 1 dimension, all I've got to do is find an equation of motion that has final position in it, but doesn't have time. I know everything else there is to know. So I'll do that. I'll use the position equation. That's the one that has final position, but not the time. And since I'm working in the Y direction, this is my generic equation. But what's going to happen is I'm only going to care about the Y components of each of these things. So I want to have the Y component of R, which is going to be the final height. I'm going to call that Y final, and that's what I'm solving for. R initial, though, is 0. Right, V initial times T. Well, remember, the total velocity was 10. But we broke that into components, and right now I only care about the Y component. The Y component of the initial velocity is 5. So 5t. Oh, but wait a second. Oh, no. Here I've got 1/2 times A, and A is 9.8. I'm going to write that as G. So negative 1/2 G T squared. I've made a mistake. What mistake have I made? I picked an equation that had 2 unknowns in it. I can't solve that yet. That sucks. But what about my other equations? I want to avoid T, right? What I should have done is taken what I call the stopping distance equation. I replaced the x's with y's because we're going in the y direction. So this is really v final in the x direction, or in the, excuse me, the y direction, v initial in the y direction, the acceleration in the y direction. I'm using only the y components of each of those things. And I'll use that because this, I've got all of that information. V final in the y direction, so here's v final in the y direction is 0. V initial in the y direction, so here's V initial in the y direction, that's 5, plus 2 times A in the y direction, here's A in the y direction, that's G, or 9.8. Y final in the y direction is what I'm solving for. Y initial is just 0. So now what's going to happen is, oops, that's negative 9.8. So I'm going to move all this to the other side. That's going to become positive. So I'll have 2 times 9.8 is 19.6. times y final equals 5 squared, which is 25. And I'm done. So this football is going to travel a height of 1.28 meters. Super easy. That's all there is to it, right? It's every bit the same as what we would have done previously. We just have to break down the inventories a little bit more fastidiously. And sometimes we may end up having to use information from both of those inventories at the same time. Let's change it up a little bit. What if I wanted to figure out something like the following? So I grew up in West Texas. And if you grow up in West Texas, you are required by law, I didn't make this law up, to be a fan of the Dallas Cowboys. I don't want to be, but I have to be. It's required by law. I must be a fan. And every year, invariably, I will see the quarterback for the Cowboys, presently Dak Prescott, throw passes to other members of the Cowboys squad and get intercepted. Now, why is that happening? Well, maybe this is Dak over here, and Dak wants to throw to their receiver. But what's going to happen is he's got to throw over some guy in the middle. So Dak throws the ball with some starting velocity. And he's trying to target this guy over here. But he wants to make sure the ball is high enough that this guy can't just jump up and grab it. So let's say that his receiver is 15 meters away. That's a pretty long pass. And he's throwing this ball at a velocity of 10 meters per second. Actually, let's specify the angle. Let's solve for the velocity. How hard does Dak have to throw this ball to get this ball to his receiver, who is 15 meters away? And let's assume, for simplicity's sake, that he's going to throw it from some starting height, but the guy is going to catch it at that exact same height. So that's what we want. He's going to throw it at a 30-degree angle. We're going to solve for the speed he has to throw it with to get it to his receiver 15 meters away. Then once we know that, we'll figure out how high does this guy have to jump to catch that, assuming that the attempted guy to intercept is only 10 meters away from Dak. So let's play this out. First, let's ignore the interceptor for a second. Let's think about how hard he's going to have to throw to hit this guy over here. So we've got a picture. Let's do the same breakdown of my kinematic variables, except now they're vectors. Somewhere on this picture, I have to call 0, 0. And a lot of times I would pick the ground to be 0, 0. But since I'm starting at a certain height and I'm ending at a certain height, and I didn't tell you how tall Dak Prescott was, who cares? Let's just have this spot right here where the ball starts. Let's call that place 0, 0. So here's my x-axis. It's actually going to be however high above the ground, whatever. We'll call that 0, 0. So I can always start my ball at a position 0, 0 for both. Super easy. Now, the receiver is ahead of him. He's forward in the x direction, but he's at the same height. So his y position is still 0. So this will be 15 meters in the, that's an I, not a J, plus 0 for J. Right? That's the position of the receiver. Now, what about V initial? Well, this is annoying because I don't know what V initial is. Before we had a number, 10, right? But now what's going to happen is I've got this stupid, I don't know how long arrow making a 30-degree angle. It's got to have an X component, a Y component. How do I split that in parts when I only know an angle and nothing else? Well, when in doubt, just assign a letter to the thing you're trying to solve for. I'm trying to solve for V initial. And I know that no matter what, this part right here is the adjacent part of the triangle. That's going to be V initial times the cosine of 30. So that's a number I just can't figure out yet because I don't know V initial, but I can still put this entire expression in for the X component. And by the same logic, the Y component would be V initial times the sine of 30. Piece of cake. Now, what about the final velocity? Do I know how fast this ball is traveling when the dude catches it? I don't, right? I figure it's probably going to be traveling down and to the right, but I really don't know the components. So both of these, I'm going to leave blank. Conveniently, the football is being affected by gravity and nothing else. So the acceleration is not sideways. But it's G, or 9.8, in the Y direction. And it's going to take a certain amount of time for that football to reach the dude. So there's my set of original items. And now the question is, how do I solve the problem now? All right, what am I looking for? I'm looking for V initial. And V initial appears twice, once here and once here. So either the X or the Y direction might be helpful in solving this problem. And it's not immediately clear to me which one is which. Let's try the Y direction because it totally worked for us last time. Right? Do I have enough information to use the Y direction of this inventory to solve this problem? Well, in the Y direction, I know the starting position, the ending position. I know the, well, sort of the starting velocity has the thing I'm solving for in it. So I need this to be in it, but I don't know this or this. So I'd have to have an equation of motion that has the initial velocity in it, but I'd have to avoid the final velocity and the time. And if you look at that list of equations, you're going to find that none of them are going to fit the bill. You know, every equation is going to have one or the other of these two things. So I'm kind of stuck. So the Y half of this inventory is a dead end. What about the X part of this inventory? Well, for there, I've got the starting and ending position. I need to have this because that's the thing I'm solving for. But I'm still missing the same two things. So what's going to kill me here is that I don't have enough information to just plug and chug in either the X or the Y direction. I need to do a little better. And in order for me to get past this little roadblock, what I'm going to rely on is that these two sides of the inventory have one thing in common, and that's time. Time connects those two things. So what I'm going to do is I'm going to switch my process up a little bit. Rather than look for an equation that has the thing that I'm trying to solve for, which is my initial velocity, and avoids all the things I don't know, I'm instead going to intentionally pick an equation that has t in it. And what I could do is I'll get one equation from the X direction and another equation from the Y direction. They'll both have t's in them. So I won't be able to solve them outright. But if I use one of those equations to eliminate t from the other equation, then I should be able to solve. Let's see how it works. So in this example, If I go in the x direction, I'm looking for an equation of motion. I want it to have v initial. I'm going to go ahead and let it have t in it, but I still want to avoid v final. I don't want to add any additional things that I don't already know besides t. So that's the position equation. So the position equation is x final equals x initial plus v initial t plus 1/2 a t squared. I'm doing it in the x direction, so the initial position is 0. The final position is, I'll call it x final, but I know I can plug in 15 in a minute. I like to plug my numbers in at the end. Makes my life easier. Now, v initial, I don't have a number for, but I have an expression for it. I'm going to plug that whole expression in. So I'm going to have v initial cosine of 30 times whatever t is. And in the x direction, the acceleration is just 0. So that whole term drops out. So this equation is true in the x direction. I can't get a number for it because I know this is 15, but I don't know this and I don't know this. There's still two unknowns. All right, so I have an equation for the x direction. Let's do it in the y direction now. So in the y direction, I'm going to have the final y position equals the starting y position plus just the initial velocity in the y direction times t plus 1/2 times the acceleration in the y direction times t squared. Now, what's the final position in the y direction? Well, here's final position, y direction, that's 0. Starting position in the y direction, also 0. So should have even written that. V initial in the y. There's V initial. Here's the y part. I just want this. So plus V initial sine 30 times t. And then I have 1/2 ay t squared. Ay, here's a, y direction, is negative g. So minus 1/2 g t squared. And again, I can't solve this problem because I have t, which I don't know, and v initial, which I don't know. But between this equation and this equation, I have two equations and two unknowns. That is a solvable system. I can totally do that. So let's do that. Let's put the two equations together and end up solving. Now, let's write them side by side. So I've got x equals v initial cosine 30 times t, and 0 equals v initial sine 30t minus 1/2 g t squared. So if I'm looking for how to solve these two things simultaneously, the thing that I need to eliminate is t. So what I'm going to do is I'm going to take one of the equations, and it doesn't especially matter which one, and I'm going to solve that equation for t. And I'm going to look at this guy over here. First thing I notice is that there's a t here and a t there. If I divide everything by t, 0 divided by t is still 0. This divided by t cancels that. This divided by t cancels one of those. Even though it's a quadratic, it's like a quadratic that factors, basically. I could just eliminate one of those values of t. Now I could solve this for t, move that over. I have 1/2 gt, not squared anymore, equals v initial times the sine of 30. I'm going to multiply both sides by 2. That'll get rid of the 1/2. I'll divide both sides by g. That'll get rid of the g. So I'll have t is equal to v initial times 2 sine of 30 divided by g. So I've just solved that for t. But now I can take that expression for t and plug that back in over here. So I have x equals v initial times cosine of 30 times t, which is 2v initial sine 30 all over g. Pretty nifty. So x final, I have v initial times v initial. That's going to be 2v initial squared sine 30 cosine 30 divided by g. And I want to pause for a second. Normally I do this as an example on its own, but since we're here, I want to point out something that's kind of cool. It'll be important later. Now, you'll notice that right now I haven't made any assumptions about the specific numbers in this problem, except for one thing, and that's that I've assumed that I'm throwing a projectile, I'm throwing a ball, it's starting at a certain height, it's coming back to its same height. And I made an assumption about the angle that I'm kicking it at or throwing it at, but notice I have the sine and the cosine of whatever angle that is. So even if I were to throw it at a different angle, I would have this same equation, but with a different number in for the sine or the cosine. And I want to simplify something down real quick. I have 2 sine something, cosine something. And if you remember when you guys took trigonometry, you learned a ton of trigonometric identities. And you've then probably forgot them all because you didn't need them again. But this is kind of cool because one of the trigonometric identities that we learned back in pre-calculus was that if I have 2 times the sine of something times the cosine of that same thing, that was equal to the sine of 2 times theta. They call that the double angle identity. And what I've got right here is that my final position in the x direction is 2 times my starting velocity squared times the sine of whatever angle I threw it at times the cosine of whatever angle I threw it at. I have 2 sine 30 cosine 30. I have all of this. I could replace that with that. So I could write this very generally as 2v initial squared times the sine of 2 times whatever my starting angle was over g. Let's remember this. This is cool because this is going to be generally true anytime I have an object that I've kicked or thrown and I've thrown it diagonally and it started at some height and it comes back to its final height. We call this the range equation. And it tells you the horizontal distance that an object's going to go. Now, why might I need this? Well, if you're Dak Prescott, if you know what angle you threw it at, and you know how hard you threw it, you'll know how far the pass is going to go. In the Army, they have you know what a mortar is? A mortar is a kind of weapon, and it's really simple. It's a tube. And you put a rock, a little bob, in the tube, and it shoots out, and it always shoots out of the tube at the same speed. And so the idea is you want to rain your rocket and have the bob land on the bad guys and not on your friends. And so what you do is you change the angle that you put the tube at, you choose the theta, you know the starting speed, and then you can do the math and figure out where it's going to land. And so, you know, there's literally Army guys in foxholes using this same stupid equation to figure out what angle to put their mortar at so that their mortar bombs will drop in the right place and not blow up something you didn't want to blow up. So pretty neat. That might be useful down the line. And it's just the generic version of what we have right here. Now, in this problem here, x, we already know, we're solving this for v. So let's just rearrange this to get v by itself. Let's replace that sine of 30 with the sine 30 cosine 30 with the sine of 230. Oops, that 2 is gone. So it's the 2 gets folded into that. So I have v initial squared times the sine of 2 theta over g. Again, the reason the 2 is gone is because the double angle identity has a 2 already in it. So all of this got sucked up into this. And I'm solving this for v initial. So I'm going to multiply by g, so I'll have g times x divided by the sine of 2 theta equals v initial squared. That means that v initial is going to equal the square root of all that stuff. And I can evaluate this for our problem. Because in this problem, g is 9.8. Notice it's positive 9.8, not negative 9.8, because we already dealt with the minus sign up here. The x is the final position in the x direction, which, going back to our original thing, here's the final position, x direction, that's 15. Divided by the sine of 2 times 30, which is 60. And now I can just crunch the numbers. So according to this, my boy Dak Prescott needs to throw this ball with a velocity of about 13 meters per second. If he throws it this fast, then the ball will reach his receiver when he's 15 meters away. Perfect. However, we still haven't dealt with the complicating factor of the guy who's trying to intercept. If Dak throws it like this, how high is this guy going to have to jump to catch the ball when it's over his head? Well, we can still figure that out. We'll do a new problem. We'll set up a new inventory. This time the ball will start here, but we'll figure out when the ball is there as my ending position. I keep getting off screen there, I'm sorry. So we'll redo our inventory from the point of view of the interceptor and figure out how high he's going to have to jump. So what's going to be different? What's going to be the same? Some of the stuff will be very similar. So now my picture is a little bit different. Because here's Dak throwing the ball. The ball is in midair now, and my dude's going to have to jump up to get it. So he's going to have to get up here to catch the ball. However, his horizontal distance is only 10 meters. So the starting velocity of the ball is the same as it was before. So when I do my inventory, all the starting stuff hasn't changed. Starting position I can still call 0, 0. My final position, though, is going to be only 10. And he's going to have to jump up an unknown height. That's what I'm looking for. V initial, we now know V initial was 13. So it's going to be 13 cosine 30 I hat plus 13 sine 30 j hat. We know that because we figured out what V initial was in the previous problem. V final is whatever velocity the ball has when the guy catches it. I don't really know either of those. But I do know the ball is accelerating with the acceleration of gravity. I also don't know the time the ball is going to take to get to him. I figure it's going to take less time for this guy to try to intercept it than it will for the receiver to catch it, but we didn't ever actually calculate the time for the receiver to catch it, so we don't have anything to compare it to. But there's my inventory. I can still break it down the exact same way. So let's look at this. What am I solving for? I'm solving for this. What do I not know? I don't know the final velocity. I don't know the time. And once again, I run into a situation where I've got too many unknowns in the y direction. I want to have the final position, but I have to avoid the final velocity and time. That's just 3 unknowns is too many. But I have another arrow in my quiver. I can figure out the time using the x direction and then use that time in the y direction to finish the problem off. So let's go over here in the x direction. Here I know everything there is to know except for the final velocity and the time. Which equation has time but not final velocity? The position equation. So I can say that x final equals x initial plus v initial t plus 1/2 a t squared. But I'm going to use this in the x direction only. So in the x direction, the final position, so final position x direction is 10. The final position in the, or the initial position in the x direction, initial position x direction, 0. Initial velocity in the x direction, initial velocity x direction, 13 cosine 30. Times t. Then in the acceleration case, it's acceleration, x direction. Aha, that's 0, which murders that whole term. Boom, that's it. So 10 divided by 13 cosine 30. That's the time that the interceptor is going to have to reach up and catch it. And that's a number. I can calculate it. So he's got about 0.888 seconds to react. But now that I know the time, I can go back in the y direction and finish things off. Because now I'm looking for the final position. I know everything except for the final velocity, so I want to avoid that. I'll just use the position equation again. So there, my y position final equals my y position initial plus the v initial portion of y plus 1/2 a t squared. So final position in the y direction, there's final position, y direction, that's what I'm solving for. Initial position is 0. Initial velocity, y direction is 13 sine 30 times t plus 1/2 a, so that's minus 1/2 9.8 times t squared. And I can plug that value for t in both those places. And if we did this right, what we should find is that the number should be positive, because it stands to reason that if the receiver was catching it when the ball was at a height of 0, that the guy who's in front of him is going to have to jump higher than that in order to catch it. And lo and behold, it looks like this guy's going to have to make a jump of about 1.9 meters. That's a pretty hefty jump, which is good. You want to throw it high enough so that when it passes over this guy's head, it's too high for him to grab it. But by the time it gets to the receiver, it's low enough for him to grab it. So that's the sort of calculation you're going to have to make when you choose what angle you throw your ball at. All right, super easy, right? I certainly hope so. So, really, when it comes right down to it, that's the entire process of these sorts of problems. We're doing the same thing we were doing in chapter 2, but now we're keeping track of a few extra variables. If you can solve the chapter 2 problems, you can definitely solve these chapter 3 problems. They're just a little bit more involved. Now, I do want to spend a little bit of time making some generalizations about this kind of motion. And sometimes those generalizations will help you have a more intuitive sense of what the answers ought to look like so that you can maybe catch errors when you make them, or sometimes you can just take shortcuts to make things easier to break down. And to do that, what I'd like to do is to try working a problem completely generically. I want to plug any stupid numbers in anywhere, and I want to see what happens. And let's go back to one that we did sort of by accident along the way. And that was this problem of I'm starting a projectile, and I'm going to go start from some height, come back to the same height, and find the horizontal range. We already solved that problem kind of along the way to solve the other problem. And we got this range equation over here. I want to think about the behavior of that range equation for a second. I want to draw some generalizations that I could make based on the range equation. So this says that if I want to know how far my kick or throw has gone, it's going to always go whatever my starting velocity is over g times the sine of 2 times whatever angle I originally threw it at. And I want to think about, like, if I want to throw my football as far as possible, I want to make it go as far down the field as I can possibly throw it. I could choose whatever angle I want to make that throw. What angle would be best to choose? Well, obviously, if I'm trying to throw it as far as possible, I'm going to throw it with as much velocity as I can muster, right? That's going to be limited by how strong my throwing arm is. But if I throw it as hard as possible, this number will be the biggest I can possibly make it. Now, g, that's the acceleration of gravity. I can't do anything about that. I'm on the planet Earth. I'm stuck with 9.8. That's going to determine something. So if I'm trying to make this be as big as possible, I'm going to have to make this be as big as I can make it. So the question then becomes, what's the biggest that I could make this? What's the biggest that the sine of 2 theta could ever be? Well, it's a sine function. Sine functions go from as high as +1 to as low as -1. You can't get the sine of anything to ever be bigger than 1. So the biggest I could ever make this is 1. And what angle would I have to make it be 1? Well, I know that the sine of 90 degrees is 1. So if 2 times what equals 90, the answer is 45. If I throw at a 45-degree angle, this is the biggest it ever gets. And that means that's the furthest that my projectile will ever go. Pretty cool. Let's test that out. So I've got my handy-dandy simulation. What did I just do? All right, try that again. I don't want to do a portion of the screen. I want to do the whole screen. There we go. So we're going to go back to PhET, where all those fun little simulations exist. I pass it? I did. This one is pretty nifty. So according to what we just figured out, based on that projectile range equation, if I want to shoot like a cannon, say, as far as possible, then I would want to shoot it at a 45-degree angle. Let's test it out. So here's my cannon, and you can see that I can change the angle that I'm shooting my cannon at. So I'm going to crank that down to 45 degrees. There we go, 45 degrees. I'm shooting at an initial speed of, let's back that down to like 10. Let's go, okay, 12 will work, 12 will work. So let's see where my projectile lands. I'm going to shoot the cannon. And lo and behold, oh wow, I hit the bullseye right on the first try. Go me. So you'll notice that's how far it went when I shot it at 45 degrees. Now, what if I were to raise the angle of the cannon up to something higher? Let's go to 60 degrees. Now, I'm shooting at a 60-degree angle, and according to the range equation, the thing should not travel as far. Let's find out. You'll notice that my cannonball, it goes higher, but it ends up hitting the ground a shorter distance away. So far, that's exactly what I expected to see based on what the range equation was telling me. Now, if I go less than 45 degrees, it should also not go as far. Let's try that. Let's just totally at random. Let's pick 30 degrees. It's not random. I'm firing. Notice it didn't travel as far. Notice something else. When I shot it at 60 degrees and when I shot it at 30 degrees, that projectile landed at the exact same spot both times. Boy, that seems like not a coincidence. Well, why should that be? Well, the answer is in the range equation. Because wait a second. If I'm doing the sine of 2 theta, let's say that I pick 30 degrees, right? If theta is 30 degrees, then 2 theta is 60 degrees. So what's the sine of 60? Well, the sine of 60 is the square root of 3 over 2. It's about 0.866 when you work it out. Now, what if I had picked a 60-degree angle? What if theta were 60? Well, if theta was 60, 2 theta is 120. What's the sine of 120? Oh, square root of 3 over 2. So what's going to happen is, because of the way the sine function is symmetric to the x-axis, the sine of 120 and the sine of 60 both give me the same answer. It's like the unit circle, if you remember, right? Here's 60 degrees. Here is 120 degrees. And the sine is like the y component on the unit circle. I get the same number for both. But notice what else is happening, right? This unit circle trick would work for other angles too, because if I pick whatever this angle is here, there's going to be another angle like that where it would also work. So the question is, what other angle should work? And the answer is any 2 complementary angles, it will work. So, for instance, if I go back to the simulation, 30 and 60 worked great. What if I crank this thing down? Let's clear these out. Let's go back up to 18. So what if I go down to like 20 degrees? Well, I can't go to 20 because I'll do 25. So I'll shoot it at 25 degrees, and you'll see that at 25 degrees, it lands over here. Now, if I take 90 minus 25, that's going to be 65. I'll shoot it up at 65 degrees. So 25 and 65 both add up to 90. When I shoot there, they land in the same spot. If I took 40 and 50, there's 40. Notice 40 will land in a slightly different place than the previous shot. If I go up to 50 degrees, it goes higher, stays in the air longer, but it lands in the exact same spot. So because of the way that range equation behaves, any 2 angles that add up to 90, they're going to travel the same horizontal distance. Now, 45 degrees is going to go further than any other possible angles. And the closer you are to 45, the further you're going to go. So if I go way off 45, if I go like really close to like, here's 81 degrees, you'll see this one goes way up high. It stays in the air really, really long, but it's got such a small sideways velocity that it doesn't travel very far sideways before hitting the ground. If I could do 9 degrees, what would happen is it would barely go up in the air at all. It would only be in the air for a split second, but during that split second, it would travel the same distance as the 81-degree shot. That's pretty cool. And you can utilize that in a number of ways. One is that if I'm trying to make my projectile go as far as possible, what the theory says is I should pick an angle of 45 degrees, and that's going to get me the maximum amount of horizontal distance before it comes back to where I originally started it. That's pretty cool. But there's more. Now, I want to caution you that this range equation that we derived, remember that when we derived it, we assumed the object started at a certain height and it comes back to the exact same height. This only works if you're starting and ending at the same height. If I was doing a problem where I start and end at different heights, this equation won't work. I'd have to go back and do it the way we were doing in the previous examples. So don't use this in inappropriate places or you'll get giant red X's and no partial credit. I'm pretty brutal about that. But I want to do something else generic. And let's just do the most generic equation I could for a projectile ever. So I've got a projectile. It's going to start at some starting velocity. I don't care what it is. Some starting angle. I don't care what it is. It's going to start at some height. I don't care what it is. It's going to go up to some other height. I don't care what it is. And if I do the inventory for this as generically as possible, it's going to travel. Let's just call this Y1 and Y2. Let's call this X1. So what's going to happen is my initial position will be 0 for X hat. I'm going to have 0, 0 be right here. But my initial Y position is going to be, we'll call that Y naught. There we go, Y naught, Y1, that's better. I'm trying to be consistent with my nomenclature here. This will be X1 I hat plus Y1 J hat, where X1 is this distance and Y1 is this distance. V initial is going to be V initial cosine theta I hat plus V initial sine theta J hat. The final velocity, don't really know anything. The acceleration, 0 I hat G J hat. So that's going to be generally true for any projectile ever. And if I use the equations of motion in the x direction, what's going to happen is I've got 0 for my starting x position. I've got 0 for my acceleration. So the position equation would be just x final equals v initial cosine theta times t. The 1/2 t squared part would cancel, just like it did in the previous problem. In the y direction, if I do the position equation, it'll be the final y position. So y final equals y initial plus v initial sine theta t minus 1/2 g t squared. And again, that's very similar to what we had previously. And I haven't made any assumptions about what any of these numbers are. Now, let's do this. Let's get t out of here by solving this for t and plugging it in there. If I solve that for t, I get that t equals whatever x final is divided by v initial cosine theta. I'm going to plug that here and here. And this is going to look algebraically kind of messy for a second, so just bear with me. So I'm going to have y final equals y initial plus I'm going to have v initial sine theta times t, which is this, x over v initial cosine theta. Then it's going to be minus 1/2 g times this squared. So what's going to happen is I'm going to pretty this up a little bit. I have v initial divided by v initial. Cancels. I also have sine of theta divided by cosine of theta. I can replace that with a tangent. So I'm going to have y final equals y initial plus, it'll be x times the tangent of theta. Then over here, I've got all this stuff in here has to get squared. So I'm going to have x squared. I'm going to have on the bottom v initial squared cosine squared theta. I'm multiplying it by 1 over 2g, or sorry, 1/2 g. So the g is going to get kicked up to the numerator. The 2 is going to get kicked out of the denominator. So it's going to be minus gx squared over 2v initial squared cosine squared theta. This is ugly. I hate it. But the reason I'm writing this out, the reason I'm doing this is because I want to make an observation about what this equation is doing so I can make some generalizations about how these things will behave. Because look what we just got. If I want to know the final position in the y direction, the final height of my projectile, it says that the final position of my projectile is a function of how far sideways I go. If I go a certain number of meters to the side, if I pick a value for x and plug that value for x in, it'll tell me how high the projectile is at that moment. If I go further in the x direction, it'll tell me how high I am at that moment. So it's telling me what this height is as a function of x. But wait a second. Y initial, that's a number. It's a constant. It's not changing. This is a number. The tangent of theta, well, I'm picking one angle to shoot it at. And so theta is a number that's not changing. So this is x times another constant. And this looks kind of ugly, but g, that's a number. It's 9.8. 2 times v initial squared. Well, when I throw a baseball, I have to throw it at some speed. So that some speed is one number that's not changing. The cosine of the angle I threw it at, it was one number that's not changing. So all of this is another constant. So what I've got is an equation that is of the form y equals a constant, let's just call it c, plus a constant times x, so bx, plus a constant, let's just call it a, x squared. Oh my God, what is this? This is the generic form for a parabola. So what did we just prove by doing all this stupid stuff? We've just proven that the path taken by any object when you throw it diagonally is a parabola. It follows a parabolic trajectory. This is what we call the trajectory equation. Right. And it says that it's a parabola. Well, what do I know about parabolas? Right. Well, one thing I know about parabolas is that parabolas are always symmetric. That means it's going to look the same on this side as it is on this side. And that's super helpful because I can do a lot of stuff in my head. Let's go back to that Dak Prescott question for a second. So in this problem, Dak threw the ball. It got caught by some guy at the exact same height, 15 meters away. Now, where is that ball going to be at its highest point? Well, because I know this path is symmetric, what I know is that if it's going back to the same height 15 meters away, at exactly the middle, it'll be as high as it's ever going to go. I didn't have to do the whole inventory to figure that out. I could have solved it that way, but just by exploiting the symmetry, I know that when it's 7.5 meters away, it's as high as it's ever going to go. So when this guy went to intercept it, he was further away than that. The ball was already on its way back down when he tries to jump up and catch it. Nifty. So that's a cool thing that I didn't have to think about. Now, what about the velocity? How fast is this ball traveling when the dude catches it? Well, what I know is that it's symmetric. He threw it originally at, it worked out to be, I think it was 13 meters per second, right? Well, what's going to happen is it was originally going 13 meters per second diagonally up and to the right, but it's going to take a certain amount of time to slow down until its y velocity is 0. Then it's going to take that same time to come back down again, which means it's going to speed up going downward the same amount, which means over here, the velocity is going to be the same 13 that it was over there. However, instead of being 30 degrees above the horizontal, it'll be going 30 degrees below the horizontal. So this ends up being the reflection of that. How did I know that? Because of the symmetry of the problem. I could do the whole bunch of math and solve it that way, but I'd be doing additional unnecessary work. I can exploit the conceptual symmetry, get the same answer with considerably less hassle. So the whole point of this exercise is that by proving that the trajectories of thrown objects or kicked objects are parabolas, I've shown that I can use the properties of parabolas to help understand how they will behave. And I know that they will take the same amount of time coming up that they take coming back down again. All right, so in terms of stuff from chapter 2, that's the big stuff. So if you, or not chapter 3. So if you haven't already started the chapter 3 homework, you definitely want to take a crack at that over the weekend. We'll be doing a projectile motion lab tomorrow. And that should hopefully get your feet a little bit wet with the stuff. But you definitely want to have the chapter 2 homeworks mostly finished by the time Monday rolls around. All right, I'll see you guys tomorrow. Have a good day.
Quick question, Professor.
Oh, somebody showed up. I thought I was talking to an empty room. Yeah, what's up?
Yeah, do we have we have a homework due tonight, right?
That's correct. The chapter 2 homework is due this evening.
Okay.
And the chapter 3 homework is going to be due early next week, probably Monday or Tuesday.
Okay. I just want to make sure we have it due today.
Yes, I did change the due dates. They were originally due at noon because during the spring semester, I had them due at the beginning of the lab class because that's when their tests were happening.
Yeah.
But I did change that, so it should be correct now. They're due at midnight, and even after midnight rolls around, you can turn them in late. It'll just decrease the amount of credit the more you wait. So.
Okay, and also it said like there is a validation, but it's mark 100 still say missing. I don't know what I have to turn.
So what happened there, Abigail, is I have a list that I can print out of validated students, and so that assignment was there because sometimes that list is slow to update because that's being done by people in Biddle.
Okay.
So if I saw you on the list, I just gave you a mark saying, "Hey, you're validated," so it would unlock all the other stuff.
Okay.
If the list hadn't been populated and I hadn't done that, people could upload a copy of their proof of validation just to say, hey, look, I'm good, really, promise you. That's all that is. So it might say missing, but there, A, you've got credit for it. B, it's unlocked all the other stuff, so you're cool. It doesn't count toward your grade at all.
Okay, perfect.
Yeah, it's not a 4-credit assignment. It's just there as a placeholder so that people who hadn't validated couldn't do the work, because that's in an online class. you're supposed to keep all the material locked up for people who aren't validated, because God
Oh,
help you if someone who's not validated learns something, uh, that has implications. They can end up getting you for owing money at the end if you don't. So it's just to keep people who aren't validated from attending class. That's all.
okay. Okay, perfect. Thank you so much.
Yep, you're welcome. So have a good day. I'll see you guys tomorrow.
All right.